Assalamualaikum and hi. Welcome to the second part of 3.4 areas in polar coordinates. From the previous video, we already know that the area covered by the polar curves is given by half the integration from alpha to beta r squared delta theta. So for today, we try to cover the area which are enclosed within two regions. For example, in this exercise 1, we have two examples. We will try to solve both of them. Okay, for question 1, we have two polar curves, which is a cardioid and also a circle with an origin as the center. The best way to visualize this problem is we want to find the area of a region inside the cardioid but outside. So it's better for us if we manage to sketch it first, so we can get a brief idea which are the areas that we want to find. So for R1 is a cardioid, 4, 8, 4. And one more is R equals to 6. Let's say this is a 6. Okay. Which are the area which is inside the cardioid but outside the circle? As we can observe, it will be in this area. But again, which area we need to find, which is the red color one, but obviously that these two polar curves represent different areas. Identify first, this is what we call as the angle of intersection, where these two polar curves meet. This is the angle of the intersection. The thing is, we want to know first, if we want to find the alpha and beta, what is this angle represents. So let's start first with trying to devise the formula A. The formula for cardioid first, let's say I want to find half from 0 until this angle of intersection. Let's say the name is beta first. Then obviously it will be 4 plus 4 cos theta squared delta theta. But where is the area which is actually covered by from 0 until beta? It will be this area. The orange color one. But we still left with this part, the circle part here. So the strategy is to find the area of cardioid on the orange color one, then you should minus half 0 to beta, and this time is 6 squared delta theta. Now what is the point of intersection here and how to find it? Is basically we equate R1 equals to R2. Therefore 4 plus 4 cos theta equals to 6. And theta will be pi over 3. So this beta is known already. and you need to find this area. But just now I mentioned that this is the area that is covered by this orange region, but don't forget we have another one at the bottom. As this cadiot and this circle is symmetric at ray theta equals to 0, you can, whether you trying to do this, then you need to multiply with 2, or if you want to find it directly, there's another strategy, which is to find directly from negative pi over 3 up until pi over 3. If you follow the second strategy, you don't need to multiply by 2. I will follow the first strategy because 0 has many specialties. For example, cos 0 is 1 and sine 0 is 1. So that's why I opt more to the first strategy, but as always, do not forget to multiply 2 at the end. So let's make this a little bit large. So obviously right now we have two areas that we need to dissect, which is this one. Let's name this A1 and let's name this A2. We need to minus A2 from A1 and then we need to multiply by 2. Obviously this is a very long working that needs to be done. If you cannot remember how to do this integration, please refer to the previous video. So let's start first with the cadiot. Half 0 pi over 3, 4 plus 4 cos theta squared theta theta. You square first, becomes 16 plus 32 cos theta 16 cos squared theta theta theta. Next, it's better for you to change the cos squared theta there. Do not integrate yet, but by using the identities, it is known that cos squared theta is equals to 1 plus cos 2 theta over 2 theta theta. Simplify first to make your integration much more easier later. 8 cos 2 theta theta theta. So this will be 8 plus 16 here. Later it will translate to 24. I will do the integration. 24 just now becomes 24 theta plus 32 sine theta plus 8 sine 2 theta. Because this is a double angle, you need to divide it further by 2, so it becomes 4 sine 2 theta. After you finish this, then you substitute the value of pi over 3 and 0 there. We settled for pi over 3 first. Then you need to minus by 0. Okay, then you will get half 8 pi for the first bracket plus 16 square root 3 plus 2 square root 3, and the next bracket is easy. It will be 0 plus 0 plus 0 becomes minus 0. So at the end you will get the first area will be times half becomes 8 4 pi plus 9 square root 3 unit squared. And this is only for the first area. Let's take a look. Okay, the whole solution for the first area. Then the second area might be much more easier. From pi over 3, from 0 to until pi over 3, you need to integrate 6 squared delta theta. So it becomes half pi over 3, 0, integrate 36 delta theta. The integration is much more easier for this constant. And you replace the value starting from the pi over 3, and then you minus 26 times 0. So it becomes half 12 pi minus 0, half 12 pi minus 0, it becomes 6 pi. As I opt for the first strategies now, I need to take A1 minus A2 and then I multiply with 2. So I take A1 right now, A1 4 pi plus 9 square root 3 minus 6 pi times 2. Therefore it will be 9 square root 3 minus 2 pi times 2, and the final answer will be 18 square root 3 minus 4 pi unit squared. This will be the area which is as enclosed in the cardioid but outside the circle. Okay, represented by the red color region. Now let's move forward to the second example. This time is the area enclosed by R1 equals to 2 and R2 equals to 4 sine theta. It is area which is enclosed by both of these polar curves. So let's take a look at how it will come out. So for the R1, the diameter is 2. Okay. Okay, imagine this is symmetric one. And for the second polar curve, 4 sine theta, it will be 1, 2, 3, 4. Okay, I try to make it much more realistic. Okay. The area which is enclosed by both of these polar curves should be this area, the right and the left. It is symmetric at ray theta equals to pi over 2. But obviously, when you take a look here, what is the point of the intersection here? Okay, so if we want to dissect these 2 points, you need to find the area from here. You need to plus with the top one. This first area at the bottom is the area, I take it back. The area at the top here is the area covered by R1 from this point of intersection until pi over 2. Whereas the area at the bottom one is the area covered by R2 for sine theta from 0 up until the point of the intersection. So let's try to represent this in the form of the formula. The formula is half integration r squared delta theta, but this time why not we try to find the point of intersection first, so I can directly write the beta or alpha there. So you equate r1 equals to r2, so 2 for sine theta equals to 2 over 4, 1 over 2, theta equals to pi over 3, I suppose. Pi over 6, just now is okay, pi over 6. So we start with the first area at the top. It will be half from pi over 6 until pi over 2. This is for R1, 2 squared delta theta. And for this example, you need to plus. Not all example must be minus, by the way. Sometimes it involves plus, and a very good imagination there. Alright, for the first one on the top, settled, and then you do plus half from 0 until pi over 6, the point of intersection, for sine theta theta. And I still opt for the first strategy. I want to find the area on the right first, and because it is symmetric at rate theta equals to pi over 2, at the end I need to multiply with 2 at the end. Okay, similar as the previous example, you need to solve one by one. Let's say this is the first area, A1, and this is the A2, and then you multiply by 2. For A1, okay, so it will be half from pi over 6 until pi over 2, the integration 2 squared delta theta. Okay, this one is easy. For delta theta, integrate it directly, becomes 4 theta. Then you replace in the values. We start with pi over 2 first, and then you minus 4 pi over 6. If you calculate this carefully, you will get 4 pi over 3 and becomes 2 pi over 3 unit squared. And let's try to find A2. Okay, A2 half from 0 until pi over 6, okay, for sine theta squared delta theta sine squared theta. By using the trigonometric properties, you need to change sine squared theta. It's equivalent to 1 minus cos 2 theta over 2 delta theta. Simplify it first to ensure that it will be much more easy to integrate. Becomes 16, 8 minus 8 cos 2 theta. Then you can integrate. This one becomes 8 theta. Integrate cos becomes sine. 8 sine 2 theta. The existence of double angle need to divide by 2 becomes 4 sine 2 theta. Replace the value starting with pi over 6 minus 8 times 0 minus 4 sine 2 times 0. Close. So it will become half 4 pi over 3 minus 2 square root 3 minus 0, so you can ignore that one, and it becomes 4 pi over 6, 2 pi over 3 minus square root 3. We already get A1 and we already get A2. So let's go back to the initial one. A1 minus A2, and then you multiply by 2. So you take 2 pi, sorry. 2 pi over 3 plus the second area is 2 pi over 3 minus square root 3 times 2. So it becomes 4 pi over 3 minus 3 square root 3 times 2, and the area will become 8 pi over 3 minus 2 square root 3 unit square. So let's take a look for the full solution. Starting with, we need to sketch so we can know which area that will be covered. So, and again, we can also know the parameter of alpha and beta there, whereas it will be we need to minus, or we need to sum the areas. For example 1, we need to minus. For the second example, as you can see here, we need to add it with different alpha and beta, by the way. For the first approach, we need to add up it first, then we multiply by 2 at the end. We solve each area separately first before you combine it together. And if you calculate it carefully, then you can get the final answer. A few tips is that when I realized that some of the previous student, the angle, for example, if you get pi over 3, you leave it as a fraction and you don't need to convert it into degree. The calculation in the form of a radian is much more preferable, and it is much more easy to calculate. Leave it in a radian and also in the form of fraction. Okay, that's all for this video. I advise you to practice your integration as well as the different combinations of polar curves. Until we meet again on the next video.